The first talk of this afternoon is by Leonardo Cavenaghi about how atoms meet symbols.
Yeah. Just start my
What?
All right, so thank you very much for you all attending here. Like a huge honor. I never expected, to be honest. I'll try to do my best, and in the same way as Tony, I don't have some kind of anecdote, but I can say that for a Brazilian, that soccer is like playing the Real Madrid with Ronaldo to collaborate with Maxine. So the purpose of this talk is indeed try to extend some of the foundational setup from atom theory, also combined with another theory developed by Maxine with Tschinkel and Beston regarding what's named modular scene. And the way Ludwig presented the atom theory to me the first time and other times was really about birational geometry. So I really expect to make this birational geometry talk now. All right. So we'll establish some conventions along the talk, just to make the notation less cumbersome. How long? We always be interest on smooth projective algebraic variants over C throughout the talk, and essentially dimension 2 and 3. All right. To avoid some technicalities, we shall consider indeed the smooth projective variants, algebraic variants, with actions, regular automorphism actions of the finite cyclic group ZP for P of prime number. And here often we shall denote by X with this power ZP, the fixed point center. All right. And the idea is then try to merge these two a priori non-expected to be combined theories in a joint theory, so atoms between symbols. And to that, I'll try to introduce to you the needed concepts of both theories and make this very much geometric, at least the way that I try to see it. All right. So then I must recall to begin with that whenever we consider two smooth projective algebraic variants X and X prime that have the ZP by regular automorphism genetically free actions, we shall say that they are birationally ZP birationally equivalent. If one can find a birational morphism between them, that's equivariant for the actions on both space. And some known obstructions regarding this is that, for instance, if you do have some equivariant birational morphism between two smooth projective algebraic varieties, since the group is ZP, then this fixed point set here is non-empty if and only if the same holds for X prime. Another quite common one is about something that's named stable linear actions for linear actions, and then this smooth projective variety being stable variation equivalent to projective space with linear actions. And the condition is that if your pick X prime to be, for instance, some projective space with some linear actions, and up to multiplying both factors by the same Pn, projective space with trivial action, if they're birationally equivalent for choice of linear actions on X prime being projective space with a linear action, then this quantity should be 0 for all subgroups of your group. Okay. And the idea in this talk is to construct new kind of ZP birational variants. And to that, we shall be interested on building quantities that are invariant under equivariant blow-up. This is because the weak factorization theorem says that we can connect these two smooth projective varieties by the sequence of blow-ups and blow-downs. And whenever I say ZP equivariant blow-up, I only mean blow-up along some smooth closed center of codimension R greater than or equal than 2. That's invariant under the ZP action. Nothing but this. Okay. So to warm up, Let's state the first theorem. Now we are in the setting of a surface, a smooth projective algebraic surface with generically free Z2 actions. Then, if you consider this quantity here, that's like the Euler characteristic of your fixed point set. This is topological Euler characteristic. And then when you look to the fixed point set decomposition, you consider all of the irreducible components that are isomorphic to P1. You look to their normal bundle inside of your surface, collect their degree, make the summation, and the claim is that this quantity is a two-birational invariant. It doesn't change under blow-ups on smooth centers that are Z2 invariant. For example, if you pick this Clebsch surface, is this cubic surface defined by this equation, we shall see the coordinate Ctn of P3, and we shall consider the natural evolution here. And that's like you exchange the first and second coordinates, and also like the third and fourth coordinates. You can check that the fixed locus in this case consists of precisely like passing franchise and etc. Only 3 points, and hence the fixed point set has only 3 points. There is no rational curves. In this invariant here on our theorem is just the Euler characteristic of these 3 points. So our invariant shall be precisely the number 3. All right, this is how it works. Yes.
So is this kind of like equivalent to having a branch power over?
You know, I'm not so sure, to be honest. I never thought this way, to be honest, but it could be. I don't know the answer.
I see.
Okay, I really don't know. I really spot this like this geometrical way. And the second, also for a surface, invariant is that you pick your surface with now ZP action, indeed, and you consider this strange quantity, this Euler characteristic of the fixed point set shall kept in the formula. But now you look to the super trace for the action of any generator of ZP in cohomology. All right, so we're seeing the cohomology really like super vector space. You look to the action and you take the super trace, and the claim is that this is also a ZP birational invariant. But it turns out that if we restrict to P equal to 2, then this quantity is Z2 birational invariant only for P equal to 2. And of course, like the previous theorem can be obtained by summation. Okay, so this is a combination of the other characteristic of the fixed point set with the super trace for in P prime. And when P equals to 2, then indeed we can go back to these degrees of these normal values. To give you an example, we consider this. Yeah, comments, questions?
Fixed point locus is a rule.
Yeah, it's mostly, yeah, we're considering mostly linear genetically free arms.
But for different generators, the same environment?
Yeah, the same invariant. So one example, we consider this multi-degree hypersurface sitting inside of P1 cross P1 cross P1, and it's obtained by the means of the blow-up of P2 at 3 general points. And since this surface is sitting inside of this P1 cross P1 cross P1, we can consider this 3 action induced on leads that simply permutes the P1 factors, right? So the fixed point set in this case is also 3, but now as we have P equals to 3, we cannot use this degree of normal bundle invariant. We should rely, for instance, on this super trace and the computation that this is precisely 2, and hence the invariant given by this second theorem is 1. Okay. Now I want to make a dramatic pause. That's in the following sense. The first time that we were working and Maxime guessed these formulas, I asked him if you knew, like, if you knew this formula, like, already, how would you know that this is birational invariant? Because you see, these formulas can sound like quite a bit arbitrary in some way, but the main point is that this theory here that we are developing works very much well as like a manufacturer to make the valid invariants that wouldn't be unexpected. But as soon as you have these formulas to prove that they are like ZP or Z2 birational invariants, you just check manually by considering all the possible block cases. But derivation, like the guessing of this formula, is obtained by the means of this construction I intend to explain that happens with symbols. But once the formula is established, you can prove like as an algebraic geometry would prove. Now, the case of threefolds. This is like a bit more interesting statement. You pick your smooth, irreducible projective threefolds with a regular genetically free ZP action, and now you fix a curve. Smooth curve of genus greater or equal than 1, and you shall collect this strange quantity here, built out the fixed point set. You take minus the number of components, irreducible components on your fixed point set that are isomorphic to C, to your curve, that you fix the free one. Then you take minus 2 times the amount of components that are surface components on the fixed point set, because this is three-dimensional, so the fixed point set will include components are points, curves or surface. You look to these components that are birational equivalent to these P1 bundles over the curve. And this strange quantity that are like the amount of ZP atoms appearing that are made out of X. I'll try to explain this. This is one of my goals in this talk that carry trivial ZP actions. So I will this like ZP atoms that are isomorphic to perfect complexes with trivial actions. I'll do my best to try to say what does it mean. Luckily enough, I have like the four founding fathers of the atom theory here to correct me and help me. So we start to constructing this theory that will gives us these invariants, these invalid invariants, and many others in many ways. And to that, I recall this symbol group construction due to Maxine and Tschinkel and Pesson. And in full generality, if you pick a finite abelian group, you consider like the character group. The idea is to build a Z model built out of these characters, for the character group. From that, you can derive some G equivalent birational invariants, so G birational invariants. And the idea is indeed collect all the possible characters, then you fix some n that a posteriori shall be the dimension of the variables that we're considering. So in this talk, for instance, 2 or 3. You shall consider these characters, you put them on uppos, you ask them to the characters chosen such that they generate the character group, and you impose some relations, for instance, that like they are invariant under permutation, any permutation. And also this a bit strange relation that has to do with all the possible choices of characters that generate your character group under some strange sums. But what is hidden, the secret, at least in my understanding, when I read the paper, is that this is scooped to make a quantity that shall be invariant under equivariant floor. So you need to know how these things shall behave under equivariant blow-up when you get a quantity that's obtained from a variety. In any case, your group BM G here, that's built out of these characters modeled by these relations, it's like Z model. So you first consider the free abelian group generated with characters modeled by these two relations, and you may ask with what do the group good for? And the point is that we pick n equal to 1. This group has a very simple description. Now we pick ZD. D means not to be prime, and your group is precisely this model that you're considering is precisely Z to the power of phi, where phi is the order of the function. So there is some hidden like arithmetic in this story. And I compiled some table here for many values of P, but now we are in N equal to 2. If you pick P equals to 2, then this is like the trivial group. If you pick P equals to 3, this is Z, then Z squared, Z cubed, sum with Z2. And here we already have like some elements of finite order appearing that does not appear like until P equals to 5. And you can try to compute all of them and recognize this model as some more familiar group. But how then you can associate with variety a quantity on this 20Z model that shall give you indeed a birational environment? This is not that difficult. You pick any smooth projective variety here. We agreed to be in dimension 2 or 3, but there's no need for that. And we look to the fixed point decomposition, look to the irreducible components. Now, for any point that you pick on a fixed irreducible component, you can look to the tangent space at this point. So I'm back at the point there is. So here we have the fixed point decomposition in irreducible components. Now you pick for each alpha a point, x alpha, and you look to the decomposition of the tangent space at this point regarding the characters of the induced action from the fixed point set. And then you assign for these characters that you collected a class on the group, summing over all of the reducible components. This gives us this quantity that shall be a G birational line. So then you give me a variety, you associate with this quantity. And now, once this is done, you can perform these equivalent blow-ups and check that this is invariant. And once you do this, you need to understand the behavior of these characters for the possible new fixed point sets that appear in the blow-up. Once you collect this, the algebraic relation defining the Z model is that what provides you indeed a genuine birational line. And now we must go to this atom theory part to try to at least introduce the needed concepts to explain the statement of the theorem 3. And that's my words, that are not their words. So please say if there's anything. I understand this atom theory as a formula. So there is no such a thing as one atom theory, like a formula. In the sense that you need some ingredients, and once you're given the ingredients, you can work on the settlement. So atom theory is really about like the choice of some view from our theory. These are bundles that Professor you explained to us, and some non-perfect group-like actions. I'll make myself very precise in all of this. Something that plays a crucial role regarding these F bundles is the F bundle decomposition, that you explained to us. And so just to refresh a bit mind, I'll be less abstract in this, but as Sonia explained to us, if you pick this D, fancy D here, just say that the germ of the zero, and you pick this to be some K analytic closed unit this coordinate U, where here K shall be some non-Archimedean field that I'll try to make very concrete in some moments. Then this F bundle shall be a K rigid analytic F. A K rigid analytic F bundle shall be a triple consisting of like a smooth K analytic super variety or a germ of the smooth K analytic super variety along some even closed smooth K analytic super variety. We pick H to be a K analytic super vector bundle, and we have this metamorph flat connection with those at most at this B plus D, and such that for any locally defined vector field, these operators are regular, have no faults. This is just what told to us. And this result of Yu, Zhang, and Zhang that was stated also in the morning says that whenever you have this special kind of decomposition of some fiber of your F bundle that's stable under the action of this guy, that the one like people that really use it to think about like the Euler vector fields, this is like the Euler vector field. Then you can extend this from one fiber to full F bundles. And to get some variational invariant or like variational geometry applications out of this story, you need to choose like appropriate F bundles. And hence understand how they behave under blow-up, how these F bundles behave under blow-up. And this is more or less what I'm going to explain here. We are always fixing this X to be smooth projective variety. We pick the smooth center. This doesn't have any kind of constraint regarding the dimension of X, but in any case, for completeness, you can see that we are in dimension 3, but or 2, but there is no need for that. We denote by X tilde the blow-up of X along Z. And also you may consider, for instance, X prime to be the variety that's built out of the disjoint union of X with R minus 1 copies of Z. All right. And a crucial result in this theory is that you can always construct this maximal F bundles over both X tilde, but also over X prime. And the result is that they coincide as F bundles. Meaning, when you have blow-ups, whenever you have blow-ups, you construct these F bundles. These F bundles shall decompose as F bundles for your variety plus R or times R minus 1 copies of F bundles over the sample that you blow up. So this is really this F bundle decomposition analogous to the blow-up formula in for homology theory, for instance. But let us make these things like less abstract and more concrete, but in a very precise sense. So now I give there's going to be like some 2 or 3 slides that shall be very, very technical. And so in order to give you some hints about this, I'll try to say how do I approach these things. So Tony, you mentioned about these convergence issues. F bundles are chosen to avoid these convergence issues. They are chosen also to provide our behavior under this analytic continuations story. But as someone that was trained in differential geometry, I try always to have an example in my mind. So I always pretended that everything is convergent and I deal with these F bundles appearing in the setting of the models. And then this is just like a formal extrapolation to make sense and to avoid many of these problems appearing from the lack of convergence percent Grama with invariants. So this is what is hidden in the next slide. And now we begin to be a bit more like technical, but very, very complete and precise regarding the emergence of this kind of F bundles in the story for a very concrete case. Remember that I said that atom theory is a formalism that begins with a choice of homology theory, right? So we pick this smooth projective variety, and now we pick this homology. For instance, the homology of X with coefficients in Q. You consider linear basis of the Z2 graded polarized Q-Hodge structures associated to this homology theory. You ask, for instance, this delta I to be pure homological degree. And you establish some conditions in such a way that you choose these generators smartly so that you are trying to mimic the construction of this model in the very classical sense. And you can, for instance, by means of this Grama-Witten theory, give rise to the quantum multiplication. Here, there is nothing about the rigid analytic so far, and we are with coefficients in Q. But the main point is that we can build the analytically rigid versions of this story by passing to some non-Archimedean field. Since we are considering Q, we pass, for instance, to the field of Fussio series. Then you have really formality conditions to the convergence and analytic continuations. So from this data here that we chose, again, this is like very, very, very technical. I'm just trying to explain the ideas and put explicitly the quantities so that the ones that are really familiar can get the real flavor of the story. But you pick this dx to be, that shall be the basis of our F bundle, to be the K-ridge dynamic supermanifold built out the coordinates that we chose by choosing these generators of a few polarized Z2 structures. And then we really build this F bundle explicitly with like some remark here. This should be dx. And we are always thinking nothing like more in over that we are dealing with homologies and hence this Grama-Witten theory over Q, but over this non-Archimedean field that if you like, you can think of the 2CA field built out of these with formal variables being this one that we introduced, meaning this DJ.
The French citizens have objection. Uso, not uso.
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 Thank you. Thank you. Yeah, so we do have this, and this is like how you make this theory like complete from F bundles. You choose your homology theory. This is my understanding. Okay, you choose your homology theory, then what you need to do is pass to some non-Archimedean field. All right, and once you pass to this non-Archimedean field, you need to know that there are some Grama-Witten theory there. The guys did. Katzarkov-Kontsevich-Pantev-Yu. So they built this non-Archimedean Grama-Witten theory. From that, you can derive some kind of connection.
The Grama-Witten friends, just people.
Yeah, but the non-Archimedean field was already like
no, Archimedean field no.
In these atoms. So,
Atoms here.
yeah,
Sorry.
I'm referring to the atoms. Sorry. Yeah.
Formally.
Yeah, sure. I mean, the extension to this non-Archimedean. Yeah, sorry. Yeah. For a moment. Yeah, so so if you like the extension to this or permanent.
No, it's really nothing.
Okay, all right. Yeah, sure. I mean, I didn't know. So but in this setting, in any case, you have your quantum multiplication, then you have the analogs of Euler vector field. And now we can really like deal with these things as in standard Grama-Witten theory, but without convergence issues. Okay. And the relation of this theory of like birational geometry comes from restricting your homology, only taking the Hodge cycles. And it turns out that this gives you a clearly even closed K analytic submanifold. So this also should be dx, sorry, whose dimension is a dimension of your Hodge cycles. And you can consider the operator. Now that's the Euler vector field. You compute this at some s for s in dx Hodge, and then the quantum multiplication also on x, and you get indeed an endomorphism of the fiber of your bundle. This is what you explained to us. Turns out that this rule here, this association is lower sum continuous with respect to s.
What does it mean? It's not real. Number of eigenvalues first, so continuous, not.
Yeah. Sorry. Yeah, sorry. Not the answer. Yes, the amount of the eigenvalues of this operator. Yeah, sorry. There is this thing here. The number of eigenvalues of this operator is continuous because so this is endomorphism. So this is endomorphism like decompose with eigenvalues. Then the amount of the eigenvalues is lower sum continuous, and yeah. So here it was fixed. Sorry.
The eigenspace is going to happen.
Wait. Yeah, but so for the splitting on for the action restricted to this Hodge cycle. This is up to coding. Yeah, it's this, but that's to coding. I'll get it. But yeah, it's here. So indeed, so the amount like reach a maximum value and some analytically dense open set. And when you consider, for instance, the zero locus of the characteristic polynomial, this is a closed analytic subspace that's finite over your base of your Frobenius menu. So the thing that we do is that you start your homology theory, but now you restrict to Hodge cycles. Look to the eigenvalues of your operator there. You have like the zero locus for the polynomial characteristics, but you're indeed inside of this small Frobenius, taking some open still subset where the amount of your eigenvalues of your operator is maximum. And I can just skip this, but up to some technicality about like passing to spectral covers and this kind of things, this is what gives you this local Hodge atoms. That I'll call this one. So if you like, you can, up to some technicality, look to this generalized eigenspace for the action when you restrict to the base of your F bundle to be like only made out by Hodge cycles. Okay. And how these things can be used in birational geometry is that if you now consider this huge set, like consider all these isomorphous class of smooth projective varieties, look to this Hodge atoms modeled out by automorphism, then you have like huge set, and from them like you have their atoms corresponding, but you can model out this huge set by the blow-up relations coming from this blow-up decomposition of these F bundles. So the philosophy here is that if you are giving two smooth projective varieties, right, they shall be, if they are birational equivalent, or if they are birational, then their atoms like should, they, how can I say, it's like, they don't share, they have the same atoms up to codimension at least two, right? So this is it. They shall be birational equivalent. If they are birational equivalent, their atoms coming from this decomposition, they shall be the same at two codimension, greater or equal to. And now we are indeed ready to go back to the story after this intercourse, short intercourse on atom theory. The idea is then try to merge these two things, this Z model, to build a new Z model that built out of the combination of these symbols with atom theory. And to that we shall consider now these classes here belonging to this formally constructed group, but we are now only taking the characters or like the entries, elements on the three-dimensional of the model that I stated on the beginning, but for which no entry is zero. And they have like a geometric mean that I'll always write here, but to save some time, let's skip. We are also considering P1. So these are like symbolic stuff. I'm collecting these symbols, and now I'm collecting this kind of like generalized symbols that I put on the percentage. Then two more characters. And just to give you a taste on how they are built, is that these characters, they correspond, they should be obtained by the actions on the action of your group, that's ZP, on the tangent space at fixed points. So you have the same characters. And now you look to components that are P1s. You look to the action on the normal bundle that will have these two characters, A1 and A2. But you also collect separately curves with higher genus. But again, you look to their normal bundles, the action on their normal bundles, pick the characters. Okay. And you do this for surface, but here you collect like really birational types of surface. And then you look to the normal bundle, look to the action, collect the character. And this shall be like the generators that are symbolic, but also these atoms, generators with trivial Z actions. So you look to the atoms, because you have action in homology, you have action on this Z atoms, and you are only consider atoms that can appear up to dimension 3. So you're like making a huge Z model that's like, you really like abstract and dealing this formally. And to get some birational invariant out of this, you want your Z model to be constructed in a way that it encompass blow-up relations. So this is scary because there are many. So you have to treat case by case to know how these relations appear. And that's one of the reasons why we are up to dimension 3, because then if you have a ZP acting generically free and by regular automorphism on your right, you can decompose the fixed point set. Here we are really in dimension 3, so X is dimension 3. You can decompose these in finitely many points, irreducible curves, and irreducible surface. And this group is built by, unlike computing only the normal bundle characters, we have this thing. And to keep track of like how this symbol stuff shall be related to choose the correct block relations, we rely on this rather trivial, if you like, relation. But the important thing, the way that I see this formula is the following: we are building data from fixed point set. So when you pick fixed point set, since the exceptional divisor also have this action, Z is the center, is G invariant, we can split the fixed point set. So it's like, I always read this like the following: if you pick fixed point set, you are blocking a center, you are taking this out from the fixed point set. But it may appear on the exceptional divisor as well. So you need to keep track the contributions coming from the exceptional divisor. For instance, if Z is a fixed point set component,
Even curve.
curve. Yeah, sorry. Yeah. I just left the road. So you pick a curve to be the irreducible fixed set component. Now you look to this G representation on the normal bundle of the curve inside this three-dimensional variety. It will be with two characters, right? And if the characters are different, blowing up Z will result in two copies of Z in the fixed point set in the blower. If they coincide, they will introduce, you're keeping Z, but introducing also a surface that's birationally equivalent to ZP1. Like in pictures, if you like, so you have this invariant space for the actions. I will take the projectivizations to get the exceptional divisor. And this will split the projectivization, the exceptional divisor will split according to this linear invariant spaces by the actions, right? So it's just this. And now we turn out to the point of guessing formulas, right? The formulas, how they were guessed. Because we built as a model made out of this very, very abstract stuff in this symbolic strange generators that are variational types of surface, curves with higher genus, the symbols. How would you guess?
I'm a bit lost. There were symbols.
Yeah, the
There
symbols
were
were
the
they
atoms.
were here. One of the
And
generators.
then it did relation symbols, and then there is the atoms.
Atoms are categories. Other pieces and typically similar problem decomposition.
So when you do the log, you can rely on the log, similar to the composition formula, and so they will appear here on this log relation. But I should have said that longer. So when you consider some of the blow-ups, you may take, for instance, an irreducible curve, then you add a surface, and it will appear some atom corresponding to this perfect complexes of this curve with trivial actions. So this is encoded like, how do you compute them? Like in fact, you do this, you rely on this canonical SOD, right? And the see then by the Euler formula, how case by case it will contribute with some.
And it's easy to go from an SOD to the boundary or how.
This is a nonsense, but even if it's correspond to some pieces of some SOG defined after brain group action, so it's a way to encode, just to label things,
Okay.
label abstract sense.
This is, I guess this is what we reference like ideal versus legal picture, right? The atoms are homologies, but to keep track, you
They can go to some force theory, whatever.
Yeah, for instance, to take like the periodic discrete homology, right, of this guy, this pieces appearing This is generalized eigenspace.
So where is the perfect complex coming from?
It's our law of theorem, not just perfect complexes throughout, it's invertible decomposition of base and seven copies of
I understand.
Yeah, because we are considering as generator is this, so we also must know how these generators behave on that block. And to do this, you rely on this block from.
And then in your definition of the atoms, am I right? So the idea is that if the two singular birational outside of at least four-dimensional locus, this quantum product, the quantum product sees the difference between the two exactly at curves that lie in that locus. Am I right?
I don't know.
No, it's kind of different, yeah, it's.
So
The curves
outside of that
which
locus,
curve which passes the.
it's up to
Not
the
the
curve actually passes the
Contains.
Not so important question. Is the quantum product is a small quantum product?
No, it's all.
It's really like Grama with them, right? So, but for the next
It's
station.
not small, it's almost impossible to calculate.
Yeah, but it's like in the example, the way that I used to do this, and that's what I learned from Ludmil mostly is that maybe it's not the best way, but I try to write the lambda Hindenburg, compute critical values, then look also to the semi-orthogonal decomposition. And check. Not sure if this is most effective way, but this is how I computed with atoms.
This mysterious.
No, but I mean, two here, it's correct, have a zero or positive canonical plus, then there's only one atom.
Yeah.
Yeah, it's kind of main calculation tool, yeah.
So this formula is still very mysterious. So this number of fixed point with respect to this fixed genus curve, and then the number of surfaces given by the curve times C1, and then minus something.
Yeah, let's
Is
see.
that some kind of, can you formulate it into a Grama Witten theory problem?
To be honest, I have no idea. I
Where
can
is
tell you
it?
how we get the
Where
formula.
is this formula even?
I can tell you how we get the formula. I can tell you now in this example. So, so in this example, to make things simple, we are considering Z2 in the group because we are only getting like these generators of this B2 that are non-zero. So this only leaves us with possibility that all the characters are one. Okay. Now, when you do this, the generator corresponding to atom, we're gonna now. You asked me about how you get this formula, right, from this theory. Now, for instance, fix the curve, G, and then look to this generator. That's the perfect complex of this curve with trivial Z2 action, right? This is your generator. Now you also consider this symbolic generator of the curve, and now it shall be 1, 1. And if this curve appears, you have also to consider the third generator. So here I fixed the curve and I just wrote down all the possible generators related to this curve. So in this theorem, remember, you give me a curve in the beginning with some genus. Now what I'm doing is that I'm choosing what are the generators in the symbolic group that are related to this curve that you gave. And these are only the perfect complexes of this curve with trivial Z2 actions. And this pairs here, that shall be C, 1, 1. And the birational type of this C cross 1 with 1. And what you do now is to observe on all the relations that you what relations appear consisting of this data, like how these generators behave under the relations. And if you go back to all this huge amount of formula, you can see that the ones that have these terms, they shall be perfect with trivial actions, and then one of these two options. Either you subtract the curve, extract it, and add the variational type, or you sum. And this is a Z model. You want to construct a homomorphism to Z. This is a relation. This seems to be zero. this model. So you map this to 0. This line and this line. Okay. You just assign a all numbers. And now you're starting to put in some ways to make this divisible. Plus, minus 2, plus, minus, minus. So this is the amount, the quantity that you're looking for. Minus the number of the irreducible components isomorphic curve. Minus 2, the components that are birational to C plus 1. Plus 1, the perfect complex. So you get the formula. Simple as this. And you get the formula. So you guess the formula, and this is obtained by like this very, very complicated symbolic group where you want to choose the generators, and you understand how they behave under blow-up. So you need to know also from the atom part how they behave under blow-up. And now we just establish a more with Z. And you guess the formula. This is not the proof, right? So you guess the formula. Now you prove the formula. And this is the way that was done. And to conclude, I'll present an actual example where you can show some with no trivial Z reaction that cannot be variation equivalent to NP3 with linear Z reaction out of this. Taste how it goes. We pick a polynomial of degree greater than or equal to 4 with only simple roots. And consider the variety defined by this equation. And you shall let Z3 act on this variety by cyclically permuting x1, x2, and x3. Okay? So the fixed locus shall be the curve given by this equation. X3 equals to dy. By the choice of the degrees and only simple roots, you can check this is a curve of genus greater than or equal to 2. Then you need to compactify your variety. And this choice is such that when you compactify, you can extend this reaction, and no other fixed component is added to the fixed point set. The weights for the Z3 normal bundle representation are 1 and 2. Remember, we're on this Z3K, so we only have it 1 and 2, but you can check it there. 1 and 2. There is no such thing as atom generators in this case because this variety is rational per se. So if atoms are only atoms on Earth in space. So there cannot be an atom that is isomorphic to the atom corresponding to the perfect complex of a curve with higher genus.
In principle, it's possible if you blow up the curve. But in this case, homology all algebraic.
Yeah, yeah. So it's here.
Yeah.
This absence arises because without group action, its homology consists entirely of hard cycles. With the observation that, I should have said that, yeah. But there's no atom contribution on the formula. So our birational invariant quantity is indeed 1. And for no perfect space, so if you look on the formula, this is it only has to do with curves with positive genus. Do not appear for linear actions on 15. That's always it. So they don't have the same invariant. And cannot be Z3 variation before. And that's it. Thank you very much.